homogeneous catalytic hydrogenation. So to carry out homogeneous catalytic hydrogenation, use of complexes of rhodium and ruthenium as catalyst. Ruthenium as catalyst is required. In homogeneous catalysis, already we have read in the introductory part that the catalyst is soluble in media. Catalyst is soluble in reaction media. Catalyst is soluble in reaction media. Soluble in reaction media. So the important catalyst is Wilkinson's catalyst. Important catalyst is Wilkinson's catalyst. Wilkinson's catalyst RHCl PPH3 trice, called as chlorotris triphenyl phosphine rhodium. Chlorotris triphenyl phosphine rhodium. This is the name of the Wilkinson catalyst, and this is the formula. So how the reaction works? Reaction. This is the alkene that we are taking into consideration for reduction. It's an arbitrary alkene where R groups are there. It's a disubstituted alkene, and we are using Wilkinson catalyst. So the product is, the reduced product is RCH2, CH2R. Now the mechanism of the reaction. Two ways we can represent the mechanistic pathway. One is through catalytic loop, another one is through normal way. I will write first the normal procedure and then we will go for the catalytic cycle procedure. Both are same only. So this is the structure of the complex. A solvent molecule actually replaces a ligand. Then hydrogen will be added, leading to complex of this kind where both the hydrogens are attached to rhodium. Next, solvent molecule will be replaced by alkene. It is the eta 2 complex type. Eta 2 in organometallic chemistry, that eta 2 complex systems are there. So an alkene only is getting coordinated to form an eta 2 complex. Now the solvent will once again come and replace, and the reduction takes place with the ejection of the corresponding reduced product. Again, the cycle keeps on going like that it does. This is one way of depicting the mechanism. Another way is through the familiar catalytic cycle in organometallic chemistry. It is called as Tolman catalytic loop. Tolman catalytic loop. Here, for simplicity, I am writing L as the ligand, where L is equal to PPH3. That represents Wilkinson catalyst. Now, a solvent molecule is coming inside, and one L is moving out, leading to now hydrogen is entering, and we have now solvent molecule is moving out with the entrance of an alkene counterpart. I am taking example of ethylene. Ethylene can be reduced to ethane, and solvent is moving out. So we have a eta 2 complex double bond we have to put. It's a eta 2 complex. Eta 2 complex, where 2 electrons being donated from the alkene side. Here alkene act as a ligand. Now hydrogen migration occurs. This is H migration. Electron changes will be there, but also you can look at in few textbooks. number of electrons, how many electrons are getting changed on rhodium, that is also there. You can check it now. Now the solvent molecule enters and coordinates, because here rhodium is in a penta-coordinated state, so again hexa coordination will occur by introducing a solvent. Yes. With the ejection of molecule, now with the ejection of molecule we have now this particular complex once again gets regenerated. So the molecule CH3 is going out. This is one of the process that we could see. The reference for this particular catalytic cycle is from James E. Hohe, Inorganic Chemistry. So reference J. E. Hohe, Inorganic Chemistry. In the organometallic chemistry, you can refer. This is the catalytic cycle for Wilkinson catalyst. The solvent molecule replaces the ligand triphenyl phosphine, and then hydrogen enters. So we have a complex where rhodium is attached to hydrogen. And then the solvent molecule will be replaced by the incoming alkene. We have eta2 complex. Then hydrogen migration. One of the hydrogen is getting migrated from here to here, so that there is a formation of eta1 complex. There is the eta1 system, eta1 complex. Eta1 complex. Then again solvent is getting coordinated with the rhodium. In the last stage, you could see CH3 is alkyne is coming out. This is what it is called as Tallman catalytic loop. Tallman catalytic loop for the alkene hydrogenation. So Wilkinson catalyst has its merit. There are various merits are there for this particular Wilkinson catalyst. It can reduce C double bond C and C triple bond C, but not C double bond O or C triple bond N, that is cyanide, carbonyl and NO2. So in the presence of these groups, if C double bond C or C triple bond C is there, that can be easily reduced. Examples: NO2 group is present, so NO2 will not be reduced, it will be untouched, but this particular CH double bond CH will be reduced by the catalyst. Similarly, if cyano group is there, in presence of the catalyst, this will be reduced to cyano group will be untouched. That is one of the merit. Also, there is a selective reduction when there are more number of bonds are present. For example, a mono and disubstituted bonds are there. a mono-substituted bond will be reduced when compared to di-substituted. So it is also used for selective reduction. Selective reduction. Suppose mono and di-substituted double bonds are there. So there, together with tri-substituted and tetra-substituted, double bonds, then mono and di-substituted double bonds will be reduced. Double bonds will be reduced. So selective reduction is possible. So there will be a partial hydrogenation of compounds that we could be able to look at from the catalyst. Examples. So this, if you look at it, is more like tetra-substituted. You can say tri-substituted. There is one substituent there, another substituent there, another substituent here, and hydrogen is there, tri-substituted. Whereas this one is 1 to di-substituted. So this will be taken preference than this. So this particular double bond will be reduced. Di-substituted, and here it is 1, 2, 3, tri-substituted. So di-substituted will have the privilege for reduction. So selective reduction, partial reduction is possible. Let us look at the mono-substituted and di-substituted now. This is a mono-substituted. This particular double bond is di-substituted. Once this catalyst is present, then this will be reduced and not this. The addition is syn addition and stereospecific. Addition is syn addition and stereospecific. If you take malic acid and fumaric acid, they will give corresponding meso and diol mixture respectively. So addition is syn. Addition of hydrogen in Wilkinson catalyst, using Wilkinson catalyst, is a syn addition. Example, let us consider the addition of deuterium to malic acid in the presence of catalyst. This is malic acid. Deuterium is added in the presence of Wilkinson catalyst. It leads to a meso product. This is malic acid. This is malic acid. Now let us take fumaric acid. Then it will be a DL mixture. DL mixture. DL mixture. So the reaction is a syn addition and stereospecific. Now hydrogenation of alkynes. Hydrogenation of alkynes. First, catalytic hydrogenation. Similar to alkenes, alkynes also can be reduced using a transition metal catalyst like platinum, nickel, Raney nickel, etc. But alkynes cannot be reduced at alkene stage because the presence of active catalyst makes again alkene also to be get reduced. So the first step will be the formation of alkene after reduction, then immediately the alkene that is formed further undergo reduction to give alkane. So it is impossible to stop unless or until you have to check the reaction by adding some poison. Example, CH3. So alkene stage alone it doesn't stop. First it leads to alkene, in the second step it goes for further reduction to alkane. Here the example that we have taken is butane, that is getting reduced to butane. This is butane. Butane through one butene. So if you want to stop only at the alkene stage, we have to modify the catalyst. Then what kind of catalyst that we can able to look at? A catalyst, for example, that we can use by poisoning is Lindlar's catalyst. We can use Lindlar's catalyst so that reaction, the catalyst reactivity will be reduced by poisoning using calcium carbonate, lead acetate, Lindlar catalyst on calcium carbonate, and using lead acetate in quinoline as a poison will diminish the catalytic reactivity so that the reaction will stop only at alkene stage. Lindlar's catalyst. PD and CaCO3. CaCO3 is support here. Plus plus lead acetate, lead acetate, lead 2 acetate in quinoline, So we will represent the catalyst like PDCaCO3, PBOAC in quinoline, called Lindlar's catalyst. This particular poisoning will make the active catalyst reactivity will be suppressed, so that only up to alkene stage the product will be isolated. And alkene is also cis alkene predominantly. Cis alkene will be the product. So a double bond will be reduced to a triple bond will be reduced to a double bond by this Lindlar's catalyst. That is what that we could see. Example. The Lindlar catalyst, whatever that we are discussing, also selectively reduces only the triple bond and it doesn't touch other functional groups. Example. PDCaCO3, lead acetate in quinoline, that is collectively called as Lindlar's catalyst, gives the product OH. That's it. This is the product. Let us look at one example for the synthesis of cis olefin. For example, CH2 triple bond C, CH2 thrice, CH3 using Lindlar's catalyst and hydrogen gives C double bond C, CH2 thrice, CH3, hydrogen cis olefin in 87%. Cis 5 dozen, you can say, cis 5 dozen. This is 5 design. So it is a stereoselective reduction. It is a stereoselective reduction. Now let us look at another example. You can use heterogeneous or homogeneous catalysts for hydrogenation of alkynes. There are examples out there. Hydrogen, palladium, carbon. This is homogeneous. This is heterogeneous catalyst. Heterogeneous or homogeneous Wilkinson catalyst. Wilkinson catalyst, we can able to reduce the compound to CH CH2 bond CH3. We know already, we have discussed that alkyne bond also can be reduced by homogeneous catalyst. This is homogeneous. And we know already palladium C or hydrogen, if it is used, it can reduce the corresponding alkyne to straight alkane. In between there will be alkene formation, it doesn't stop there. In this case also it will be completely reduced using Wilkinson catalyst. Another interesting catalyst that has been reported, that is Na2B, called nickel boride. This also reduces the alkene to cis olefin. Example, alkyne to cis olefin can be done using nickel boride. So if you use nickel boride, Na2B, this is the formula, Na2B, we will be getting cis olefin. Using alkali metal also we can reduce the C triple bond C. So second one is reduction with 1A group metal with alkyne in liquid ammonia. Use of reduction, okay, with one A group metals in liquid ammonia. Group metals in liquid ammonia. Similar to Bitch reduction type, but here we are reducing a C triple bond C, and the product interestingly is trans olefin. So sodium, this 1A group metals, usually sodium, lithium, and potassium. This is what that we could see. Product is transalkane. The C triple bond C will be reduced, and the product is a transolefin. So let us look at Na in liquid ammonia. We will have a C double bond C, a transolefin, is the product. Example, you can write it as, for our convenience, R bond C triple bond C bond R. Example, CH3 CH2 C triple bond C bond CH2 bond CH3. Upon reduction with Na ammonia, liquid ammonia, that we can represent with NH3 within bracket L, gives CH2 CH3 a transolefin. Now the mechanism of the reaction of the reduction mechanism. Step 1. Similar to Bitch reduction, formation of NH3L leads to electron transfer, and we have a solvated electron. We have solvated electron that we have to consider. Solvated electron. Now this solvated electron as well as ammonia molecule will involve in the reduction of the alkyne to form the corresponding trans-alkene. How that mechanism works, let us look at C bond R. It involves radical anion as well as vinyl radical. That vinyl radical will be cis as well as trans. And the trans usually, because of less repulsive nature, forms the predominant product, that is trans-alkene. Let us look at one by one the mechanism. Now electron, solvated electron is coming, that is solvated electron that adds to that particular carbon to a radical. You could see a radical formation here that adds to an electron. So two electrons like that together are there. That means a negative charge is there. Leads to a double bond Cr minus. Now ammonia is there in the system. So a proton will be abstracted and amide anion will be moving out, leading to the formation of R bond C dot. We have to write in different way. I will write structure, then you will be understanding. C bond R, bond hydrogen. So there will be a radical. So this is a trans. This is actually a radical, that is vinyl radical cis. Vinyl radical cis. Now this will be in equilibrium with a stable trans vinyl radical where R and R will not interact, because R and R are bulky groups. If they are on the same side, there will be a repulsive force that will be unstable. So SS will be converted to a trans structure. So vinyl radical trans. Vinyl radical trans. Now solvated electron comes once again. So it makes a negative charge on that particular carbon on that particular terminus, you can say. There will be a negative charge, R bond hydrogen. Now once again ammonia molecule, from which a proton is being abstracted, and elimination of amide ion takes place to provide a trans alkene. So this is one of the interesting example of reduction of alkynes. Next, hydrogenation of aromatic rings. Catalytic hydrogenation. Alkali metal reduction, electron transfer. Two ways are there. We will be discussing only catalytic hydrogenation. Electron transfer reduction, example pitch reduction. Example pitch reduction. So we will discuss only catalytic hydrogenation in this particular class. So total hydrogen, total reduction. It is actually a total reduction. You can say. Difficult to reduce aromatic compounds because of their exceptional stability. Aromatic compounds because aromatic stabilization is lost. Because aromatic stabilization is lost. Stabilization is lost. So we need more vigorous condition. We need more vigorous conditions are needed. More vigorous conditions are needed. Conditions are needed. The condition depends on how much resonance energy for that particular substrate. It depends on how much resonance energy is there for a particular substrate. For example, one will have lower resonance energy that can be reduced faster. One will have higher resonance energy that will reduce slowly. So depending upon the resonance energy of the substrate, the conditions will be altered. Conditions will be altered based on the resonance energy. Conditions will be altered depending on the resonance energy of the substrate. Resonance energy of the substrate. For example, if you are going to reduce benzene and naphthalene, benzene have 36 kilocalorie per mole. Example, benzene has 36 kilocalorie per mole. Naphthalene, it is attached to, we can view as two fused benzene rings. Per ring has 29 kilocalorie per mole. So naphthalene can be reduced with lesser vigorous condition when compared to benzene. Benzene has 36 whereas it has 29. So a naphthalene can be better reduced easier when compared to benzene. So naphthalene on reduction gives tetrolene, whereas benzene on reduction gives cyclohexane. The best catalyst for this purpose, platinum, rhodium, ruthenium catalyst.